of the session. My colleague Tomasso Cappello, he's going to tell us about linear and power efficient RF systems. So over to you, Tomasso. Yeah, just to confirm, we got your slide share. I can't hear you, Tomasso, and I can't see that you're muted. I don't think your audio stream's working. I think your laptop can't find your microphone. Still no jaw on the sound at this end.
Can you hear me now?
Yes, can hear you now, Tomasso.
Yeah, it's same microphone I was using before. Anyway, hello everyone. My name is Tomasso Cappello. Today I'm going to talk about linear and power efficient radio frequency subsystems. So base station power budget. So if we look at a base station, especially to the transmitter side of this base station, we find out that the radio frequency unit, the radio frequency part of a base station tends to burn quite a significant amount of power. And this is especially remarkable with macro cell base stations, where the power consumption is about 3/4 of the total power budget, or the total power that you can get out of the outlet for a base station. And if we look inside the radio frequency unit of this base station, the power amplifier, which is this circuit that is used to boost the signal to the required power level to overcome the channel attenuation, the power amplifier, this circuit, implements a linearity and efficiency trade-off. So if we look at the backoff region of the power amplifier, the amplifier can be operated here with high linearity, and so possibly with a good linearity performance and low spectral occupation. However, the efficiency will be quite low in this region, especially if IP-IPR signal are utilized. If we drive the amplifier more in the compression region, then we will notice that the efficiency will be much higher, up to 50–55%. These numbers are really high for a radio frequency power amplifier. Normally, you see the commercial power amplifier typically present efficiency between 15–20% when there is an amplitude modulated signal. However, the distortion we operate in the point B will be significantly higher. And so there are several techniques published in the literature in order to overcome this trade-off. And one of them is digital predistortion. If we look inside to the transmitter architecture, they typically present a structure like this one. So especially if OFDM modulation is used. So several carriers are generated and modulated following a certain standard. Then there is a block called the class factor reduction in order to reduce the dynamic range of the amplified signal. And then some IQs, digital bit streams generated by the digital baseband of the transmitter, are then converted first in the analog domain, and then up converted at a certain radio frequency carrier, and then there is a multi-stage power amplifier, starting with a pre-driver, a driver, and a PA power amplifier that generates the signal with high power levels. Finally, also a bandpass filter can be also used in order to reduce the leakage on the NERBY channels. So if we look inside, and we find out that the PAs, so this last stage, is the major source of nonlinear memory effects. And so nonlinearity is typically manifest because of the compression of the power amplifier, and also it can present memory effects. So the history of the amplified signal somehow impacts the amplification characteristics of the PA at the current moment. And so if we look at the input spectrum or the IQ signals before the conversion from the digital to the analog domain, we can find out that, especially if the amplifier is running into compression, so for a higher efficiency, we can see that there is a significant spectral regrowth on the side skirts of the spectrum and also within the band. And starting from 4G, so when IP-IPR signals are starting to be used, there is more and more split between the capabilities of the radio frequency hardware and what instead can be offered by the digital baseband. Digital baseband is notoriously more flexible and more able to implement complex modulation schemes. The RF part instead is still limited into this. So here on this slide, it is discussed a way on how, for example, we extract the signals, the distortion characteristics of a power amplifier. And so this is typically done in the literature with sinusoidal type of approaches like the two-tone test, the multi-tone, and so on, or with pulses like rectangular pulses, like rectangular radar pulses. In this paper, it is discussed an alternative way, which employs Gaussian pulses. So the idea is to decompose the envelope of an IP-IPR signal, which is shown here in black, into a train of amplitude modulated and time shifted Gaussian pulses. So as we can see here, these approximate quite well the envelope of a signal, but the capability added for this is the way we study, the way we extract the nonlinear memory effects of a power amplifier. So for example, if we follow the red arrow here, the gain characteristics of the PA will follow more or less this contour here. And then when the signal goes down, the gain drops around 16. So here it is shown as a line, but in reality, what you see experimentally is more like a scatter plot, like dispersion points in the back of region. These are known as memory effects. And so as we reach the compression, so the maximum output power with 30 dBm input power, then amplifier normally compresses, so without much dispersion, but then it comes back here with where the gain is about 14 and 15. So this needs to be known to the digital baseband in order to correct for it with digital predistortion algorithm. And so in this work, we show that the amplification characteristics that can be extracted with Gaussian pulses are somehow similar to the characteristics of the same power amplifier that can be extracted with an LTE signal, for example. So the two methods are interchangeable. Indeed, they show a very similar behavior, but the flexibility of using a Gaussian pulse is the fact that it's a simple pulse that is very simple to implement with an arbitrary waveform generator. And so it's more like a method on how things are extracted and measured. Then, for example, this is another methodology that has been applied to a GaN duality power amplifier with 500 watt output power. This is currently used in base stations in China by Huawei. And so the power amplifier characteristics normally when it is excited with CW input signals are like this. So they follow this dashed plot with a typical Doherty hump around here, and then they go into compression. However, if the power amplifier is driven with modulated signal, because we want to transmit some information, they tend to present some dispersion in the back of region, like the ones that I've shown before. And so the idea here is to decompose, to look at the envelope of an IP-IPR signal, which is shown here, and notice that we have a number of peaks where the output voltage reaches Vmax at the transistor output, and then there are certain valleys in between. And so depending on the distance between these two peaks, the dispersion in the back of region can be higher or lower. And so we studied this by using a double pulse technique where a pre-pulse here is applied. So a pulse of radio frequency power is applied to the power amplifier to sort of prepare the power amplifier for the actual acquisition. And then there is a time between the second pulse or the measurement pulse that is used instead to extract the gain characteristics of the power amplifier. So by doing so, we are able to generate a sort of like gain recovery time and for different peaks separation. And so if this information is available, for example, to the digital predistortion at the baseband of the transmitter, it is possible to predictively update the DPD based on the separation between these two peaks. So, for example, so in blue, it is shown a flat gain of the amplifier with 13 dB of gain. This is showing in amplitude, of course. If the DPD instead is not doesn't know the fact that the amplifier changes its characteristics, it might show some recovery. So the actual amplification characteristics of the PA is the red one. So by observing this recovery time, which is due to trapping effects within the transistor, we can somehow correct for them and provide a better linearity performance. So this is about some work I've been doing with my PhD student at the University of Bristol, and is related to what happens if we pack a number of PAs within a certain area, so where they can share some temperature between each one. So, for example, within a MIMO system or a phased array. So what happens is that all these PAs are thermally coupled. So here it is reported the thermal network. So more or less these models, the influence of each temperature models how each amplifier affects the temperature of the nearby one. And so we started looking at, for example, at a single power amplifier, and then we apply an external temperature stress that can be due to the ambient temperature or the fact that other PAs here are heating up, and so they somehow are coupled with a particular PA. And so we characterized how the gain varies depending on the junction temperature, and this is between 20 and 80 degrees. For example, we consider this range, and we notice that there is about a couple of dB of gain variation, and the same can be said also for the phase. And so, but if you know in advance the fact that the gain varies based on the temperature, you can somehow compensate for it on the digital predistortion side. And so here we achieved some good results in terms of linearization performance, where there is good suppression with digital predistortion, accounting for self-heating and memory effects. Another technique that I've been working on since my PhD is called envelope tracking, and this is quite popular now in smartphones, but is still not so popular at the station side, mainly because of the power levels involved. So a PA is this device that somehow generates an amplitude and phase modulated signal around a certain carrier. And so the idea in supply modulation is somehow to improve the backoff efficiency of this PA. They typically present, an ATPA typically present a backoff efficiency with this blue trace. And so the improvement compared to the same PA without ET is between the solid blue line and the dashed blue line. And so by applying ET, there is a significant improvement, especially in the backoff region. So it's a very interesting approach. And so this has been, for example, applied to...
bring to a close then, Tomasso.
Oh, yes, I'm sorry. So I'm just finishing with this slide. So this is typically applied to a three-stage LDMOS power amplifier for 4G type of application with an envelope tracking modulator called the power DAC. The power DAC presents a multi-level topology where a number of binary scaled input supplies are combined at the output to generate 8 voltage levels. So if we look at the characteristics of this PA, which are shown here in blue for the highest supply voltage levels, these are dynamically changed at the PA drain, and this can be compensated by using digital predistortion. And but by doing so, by applying ET, the efficiency in backoff can be somehow improved, especially in the backoff region, for example, between this pink trace and this blue trace. And everything has to be somehow controlled from the digital baseband with a number of lookup tables synchronized with envelope modulator. And the final waveform here are shown here. So when digital predistortion is not used, the blue trace differs significantly from the ideal envelope of the amplified signal. Instead, when digital predistortion is used and operates synchronously with the envelope modulator, everything becomes linear, apart from some small glitches on the envelope side. So in conclusion, here so this is more or less my view regarding the future of radio frequency communication. So 3.5 semiconductor technologies are surely beneficial for this because they can implement a very high power densities, so you can pack higher power levels in a very small footprint areas. Lower capacitances means more bandwidth, much easier match. Multi-transistor architectures such as multi-LNAs, multi-PAs, and so on, in order to somehow improve the linearity efficiency trade-off. And finally, also to keep an eye on the correction of this radio frequency hardware by designing a DPD-friendly type of power amplifiers and receivers. So finally, some fundamental research is still required to develop next generation RF transceivers. This brings me to an end.
Thank you very much, Tomasso. So certainly some exciting technology backed up by experimentation, much to share and not much time to do it.
Yeah.
Right, if the audience got any questions, please type them into the Q&A box. But I could start. Tomasso, you're showing obviously digital signal processing to correct the distortion characteristics of the PA. That itself, the digital side, will burn power. Is there an overall benefit when you take it all into?
This is something actually very interesting because I've been working on this topic quite intensively. And so so if we assume that the digital baseband somehow includes, for example, an FPGA or an ASIC, we already assume that the baseband still has some ADCs and some converters. We assume there is already something. The overall power consumption of a DPD chip is not much. It's few multipliers and others, and it's quite small. If we assume that there is already, if we have to stick instead a chip purposely for correcting the transmitter linearity and so on, the power consumption can be quite significant because the FPGA have a static power consumption, have a dynamic power consumption. This is affected by the signal itself. So this brings, for example, the question, is it better like an analog predistortion where you don't require like a digital chip to do this, or is better like a digital predistortion with FPGAs or digital logic?
So there's a question in the chat box from David Butler at the BBC. What order predistortion function are you applying?
That typically depends. Doherty's are quite nasty to correct for, but I know they are used quite a lot in like in radio, in TV type of applications because they require quite a lot of power. Generally, I generally start between 5 to up to 13. Generally, you go with the odd polynomial orders for DPDs. Yeah, generally tend to implement all the memory correction with the custom type of algorithm. I know there are formulas like memory polynomial, generalized memory polynomials, and so on, where you can somehow mix memory and nonlinearities together. But this is not what I tend to do. So this is my answer.
Yeah. So from the architecture you presented briefly today, to me it looked like a fixed digital predistortion. So as the device ages, how much does its characteristics change? And is your lookup table of coefficients still valid?
So this is a very good question. So more or less every DPD system is somehow a feedback system, okay? So every feedback system has somehow a bandwidth related to it. It's not going to be like instantaneous, the change. So what happens is that you typically have a PA, you monitor the input, you monitor the output. Then when you look at the output, you somehow see that the amplification characteristics changes as a consequence of the signal, as a consequence of aging, as a consequence of memory effects, as a consequence of temperature. So there is a number of multiple things happening. And so the problem is that aging is a slow thing for definition. It's slow. It takes time to degrade. Memory effects instead is something that can happen within the envelope time, so with bandwidth. So as the PA is working, and if you are not somehow feed forward or predictive in the way you correct for it, you are never going to be able to correct the signal as it is amplified. So the best always approach for DPD is always to be predictive for something that is predictable. So implement the prediction of where it is possible, and then the aging, all the rest of things that go also in the reliability field, need instead to be somehow corrected with a feedback or so. That can be very slow.
Yeah. Thank you very much, Tomasso. Time is upon us. We must bring this session to a close. So to all the speakers, Ian, Alex, Krishna and Tomasso, a very big thank you for your time and efforts this morning. And also to the audience for your participation. We're taking a short break now. Please make use of the Remo platform for networking. And the session that we've got starting at 11 o'clock, which is back on Zoom, a series of elevator pitches from some of our PhD students within the Smart Internet Lab. So goodbye from me and have a good morning.
Bye.